Get started. Hopefully everybody can hear me. It's a real pleasure to be here this evening to tell you about the exciting events of the last year and a half. Okay, so it's a real pleasure to come back to Burlington. Of course, I got my start here. I grew up here through high school. I took my first physics classes here, was inspired to do science here, and had an amazing support structure by this community. And it's actually amazing to what extent, many of pioneers of science, space science and astrophysics have come from this part of Iowa. So it's really humbled to come back and tell you about this exciting event. And the upshot of this is that we have an entirely new way now of looking at the universe. Rather than just seeing things with our telescopes, which is light, electromagnetic radiation, we're now able to observe cataclysmic events in our universe through a new messenger, a new channel referred to as gravitational waves. And this has only been possible in the last couple years. And this connects to another exciting topic, an open topic, which is where the heaviest elements in our universe come from. Where do the precious metals, gold, silver, and platinum, come from in our universe? And what we've discovered, and what I was recognized for this recent award, is that when two objects we call neutron stars collide, they produce a spray of debris which generates these heavy elements. And we actually saw the glow from that debris last August. And so I'm here to tell you this exciting story, and I really want to convey to you, that science is not just a linear progression, that science is not just all something you read in the textbooks, but that it's a living thing, and that it's an exciting mystery that we're trying to solve. And so I'm a professor at Columbia University in New York City, and of course I owe a great deal to that institution for supporting my research. My hope is to make this a very, accessible presentation. I realize most of you are not scientists. I'm not going to have any, fancy equations. I'm hoping that 90% of you can, understand 90% of this talk. But at the end, I'm hoping you'll save up some important questions that we can have a sort of question and answer session near the end. Okay, we're going to get started. So this is the periodic table of the elements. If you've taken a high school chemistry class, you know that this is the way that we organize, scientists organize the elements. So at the top of the periodic, top of the periodic table, we have the lightest elements like hydrogen. Oops, let's see if my pointer is working to turn it on here. At the top of the periodic table, we have hydrogen and helium. But as we go down the periodic table, we go to increasingly heavier elements. We have carbon, nitrogen, and oxygen, common elements on the Earth. Some of those are responsible for life. But as we go to the bottom of the periodic table, we go to heavier and heavier elements. And one of the goals of my areas of astrophysics and nuclear astrophysics is to identify where and when in our universe these events were created. So we think that the hydrogen and helium were mostly present since the beginning of our universe from the Big Bang. But as we go down the periodic table, we know that those elements had to be created after the beginning of our universe, primarily inside of stars and in the result of cataclysmic events. But we're still trying to fill in our knowledge of where these elements come from. So you probably know that the hottest place in our solar system is in the center of our own sun. It's several tens of millions of degrees there. And in fact, what powers the light of our sun is the fact that it's so hot that when two hydrogen atoms in the center of our sun collide, they can fuse to create a helium atom. This is nuclear fusion. It releases energy, and that energy ultimately is what powers the light of our sun. And as our sun evolves, as it ages, it will get hotter inside the center of our sun. But it will never get hot enough to create any elements heavier than about oxygen. Okay? So even when our sun dies at the end of its life, it will create an ember, a hot glowing ember of carbon and oxygen, but it will never be hot enough to create any of the elements heavier than that, because the heavier elements get the hotter it has to be to fuse them to yet heavier elements. So where do the heavy elements come from? Where do the silicon and iron and things like that come from? Well, we believe that they come from the deaths and explosions of stars that are substantially more massive than our sun. So this is a so-called supernova remnant. This is a supernova explosion of a star that happened in our galaxy about 350 years ago. It was the last galactic naked eye supernova, which means if you were outside in the year 1667, you would see a star that temporarily appeared in the night sky and was bright for a few months before it faded away. And that was this exploding star. And here you're seeing the hot glowing embers of that explosion if you had X-ray eyes. So this is detected by NASA's Chandra X-ray Observatory. And this explosion, since it happened 350 million years ago, has had a chance to expand quite a bit. So now the size of this remnant of material that was ejected from that explosion is about 5 light years across. And what we believe is that the original star that created this explosion was about 17 times more massive than our sun. So what are we seeing here in these glowing X-rays? Well, what we're seeing is the colors of the X-rays essentially tell us something about what elements were created when this star exploded, what heavy elements. So for instance, when you see red X-rays, you're seeing where the silicon was produced. Yellow X-rays where sulfur was produced, calcium are the green, and iron are the purple X-rays, okay? So we're literally seeing the creation of these elements and their dispersal into space when this massive star exploded. And this is what Carl Sagan meant when he said the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interior of collapsing stars. We are all made of stardust. And what he meant was that the elements that create, that life is created from are produced, we think, in these supernova explosions. And they, of course, get dispersed into space, and they end up in the next generation of stars, the next generation of planets. So it was the supernova that happened before our sun formed that are responsible for these elements in your body. But that doesn't, so we can understand where the top of the periodic table comes from. It mostly comes from these supernova explosions. But as we go down the periodic table to the bottom, the heaviest elements, we didn't know until very recently where these came from. These include the precious metals like gold, silver, and platinum, the very heaviest elements like uranium and plutonium. You can imagine that our civilization would have evolved, very differently if these elements existed in different abundances than they do on the Earth. And so that's the fundamental question, one of them, that we've been trying to answer. So it's long been, sort of a goal of mankind to conduct alchemy, right? So alchemy in early modern Europe was a pseudoscience of transmutation, in which you would take a base metal like iron and transform it into a noble metal such as gold or silver. If you could do this, you would obviously become very rich. And the problem is that, if I take an iron nucleus, it has about 26 protons and 30 neutrons, whereas gold has about 79 protons and 118 neutrons. So gold is much more neutron rich. There are many more neutrons in gold. And so if you wanted to create gold from iron, you would have to bombard it with a lot of neutrons. And the problem is that a neutron is not stable. If I had a neutron that's not in a nucleus of an atom, it decays into a proton in 15 minutes. So you have to have some way, if I want to turn iron into gold, I have to have some site in nature which is extremely rich in neutrons, and I have to have some way to get them into these heavy elements. And that's the challenge in how nature is able to produce these heaviest elements. But there are places in nature where we know there are lots of neutrons. If I go back to this image of the Cassiopeia A supernova remnant, you may have noticed this white point in the center, this hot, glowing point. This is the core of the star that exploded. So the massive star, at the end of its life, its core imploded to form a very dense object called a neutron star, and that released enough energy to explode the outer layers of the star. And so you can literally see this little neutron star in the center of the supernova explosion. So what are neutron stars? Well, like I mentioned, they're the cores of massive stars. After they end their lives, they collapse. The core collapses to form a very, very dense object. A neutron star has roughly the mass of our sun, but it's squeezed into a radius or a diameter which is comparable to the size of New York City, which you can see in the background here. That's the little point here is where I live in New York City, just north here of Central Park. This is not, by the way, the slide you show when you come through customs back into the United States. That's a good way to get called aside for extra questioning. So these neutron stars are seen in the centers of supernova remnants, but the way they were originally discovered is as radio pulsars. So this graduate student, Jocelyn Bell, in the 1960s, was working at the University of Cambridge with her advisor, Anthony Hewish, and she detected these blips of radio emission coming from outer space, one every second. And what we later learned is that these are produced by objects, these neutron stars. So neutron stars are rotating very quickly. The Earth takes a day to rotate around, and a neutron star takes about a second. And every time its magnetic field points at the Earth, it produces a burst of radio waves. And in the 1960s, Jocelyn Bell discovered these pulsars, and we soon came to understand that they were these neutron stars. So a neutron star is very rich in neutrons, as I mentioned. They are stable because they're not a single free neutron. They're inside this very dense object. A neutron star is so dense that a teaspoon of neutron star material would weigh as much as a mountain on the Earth. Okay, so I can't even describe to you how dense a neutron star is. Okay, and they exist. Okay, amazing. Okay, so the second part of my story is about gravitational waves and Einstein's theory of gravity. So you probably are aware that in 1915, Einstein supplanted Newton's theory of gravity with a new theory of gravity. And the essential concept is that the satellite orbits the Earth not because the Earth exerts a gravitational force on the satellite, but because the presence of the Earth curves the space and time through which a satellite moves. Okay? So the way this was best described, you can describe Einstein's theory in one sentence, and by John Wheeler came up with this quote, which is that mass tells space how to curve, and space-time tells mass how to move. So in other words, the presence of a body like the Earth causes space around it to curve, and a satellite is not orbiting the Earth. A satellite is moving in a straight line, but the Earth has redefined what a straight line means. Okay, and so this was introduced. This was, it sounds like it's just a sort of play on words, but it actually introduces a number of different features that were not present in Newton's theory of gravity, and one of them is gravitational waves. I'll come to in a second. Different objects distort the space-time around them to different degrees. The sun, although very massive, is fairly low in its density, so it distorts space-time a little bit, enough to cause the Earth to orbit around it, but not too badly. But a neutron star, where you've packed the same masses in the sun into an object the size of Manhattan, it obviously distorts space-time considerably more. If I then have probably the object you're familiar with the most is a black hole. That's the most extreme distortion of space-time you can get, where you have such a dense object, so space-time is distorted to such a degree that if you get close enough to a black hole, not even an object moving at the speed of light, like light, can escape. And so stars like our sun, if they're very massive, they end up as neutron stars. If they're extremely massive, more massive than our sun, they end up as black holes. Okay, the other piece of knowledge you need to take away is that many stars are not in isolation. So our sun is somewhat unique in the sense that there's just a single star, but many stars exist in binaries. So it's not the case that the Earth orbits the sun. The Earth and the sun actually orbit a common point, which happens to be close to the center of the sun. But if you have two objects that are bound to one another in an orbit that have similar mass, then they orbit a point which is halfway between them. So for example, this is a scene from Star Wars where Luke Skywalker goes out to watch the sunset. And instead of seeing a single star set, he actually sees two suns set because he lives in a planet that is orbiting a binary star, okay, two stars that are orbiting one another. And stars themselves can be in binaries, but so can neutron stars, so can black holes. These exotic objects can also be in binaries where they are orbiting about their common center of mass. Okay, and what Einstein's theory predicts that wasn't present in Newton's theory of gravity is the fact that these orbiting stars do not orbit forever. In fact, as a result of their motion, they emit something called gravitational waves. So there's actually a distortion, a ripple in space-time that is carried away by two stars that are orbiting one another. And that gravitational wave takes away energy from the orbiting stars and causes them to in-spiral and get closer and closer together at an ever-accelerating rate. So I'm going to show you a movie of this for two black holes. So these are two black holes that are orbiting one another, and as a result of their motion, they are emitting ripples in space-time, which are carrying away energy and causing the two stars to move closer and closer together in a death spiral, which ultimately results in them merging to a single black hole. Let me show you that again. So we have two black holes that are orbiting each other, emitting gravitational waves. Initially, they move together very slowly, but as they get closer and closer, the gravitational waves get stronger and stronger, and they move faster and faster until they touch and form a single black hole. And this was a prediction of Einstein's theory of general relativity. The amazing thing is that scientists have developed the technology to measure these gravitational waves. We've built two gravitational wave detectors in North America and one in Italy. The two in North America are, one is in Livingston, Louisiana, one is in Hanford, Washington. Together they form what we call the Laser Interferometer Gravitational Wave Observatory, or LIGO for short. And the essential point, oh, did I skip over a slide? Maybe I did. Okay, well, the essential point is that if a gravitational wave from a distant merging black hole, say, passes through the Earth, it actually causes a slight distortion of the Earth. And this slight distortion of the Earth can be detected in the laboratory. This is extremely exaggerated, so don't be scared. The actual distortion is 1 part in 10 to the 21, okay? But a gravitational wave from a distant merging black hole passes through the Earth, and it can be detected if you have a very, very sensitive instrument. And that's what this LIGO interferometer is. So each of these observatories in Louisiana and Washington has two arms. They're each 3 kilometers in length. And what they do is they send a laser down both of the arms, and then they bring the two laser beams together, and they're able to measure some distance, which is a tiny fraction of the total distance. They're looking for a process called interference. So in a gravitational wave, so normally there's the two beams of the laser come back and meet, and they completely interfere destructively. So when you'll see that they basically cancel each other out. And so nothing makes it to the mirror behind them. But then a gravitational wave passes through, you'll see, and it's going to cause a change in the light that's coming through here. So their gravitational wave is coming through. It causes these ends of the mirror to wiggle, and they can detect that. It's an amazing technological engineering feat that they're able to detect this. They're able to measure the distances between these mirrors to a precision of less than 1 atom over these 3-kilometer arm lengths. It's just incredible. And I just want to say, so this concept was developed in the 1980s, and it's taken this collaboration 20 or 30 years to develop it to the point where they can detect one of these distant merging black hole systems. And that's exactly what happened in 2015. So in a distant galaxy far, far away, 2 black holes merged. They produced these gravitational waves, and they came through the detector in Washington and then in Louisiana, and they produced a signal that looks like this. So this is the 2 neutron stars that are in-spiraling, and over time you get this signal which increases in frequency and amplitude. It increases amplitude because it's getting stronger as they merge, and it increases in frequency because they're moving faster and faster. So if you could convert this gravitational wave that LIGO detected into an audio signal, it would sound like this, like a little chirp. You'll hear it again. And so that is two black holes. Oops, I'm going to turn it off now. So that is two black holes, each with about a mass of 30 times that of our sun, merging together in a galaxy several hundred million light years away. So it traveled several hundred million years, and then for less than a second or so was detected on Earth. And this discovery of gravitational waves in agreement with Einstein's theory of general relativity won these three individuals the Nobel Prize in 2017. Two of them, Thorne and Weiss, were the original inventors of this concept in the 70s, but this actual discovery took an army of people over many years. So as of now, LIGO has actually detected 6 of these merging black hole systems, okay? So the first 2 that they detected each had about 30 times the mass of our sun, and they merged to form a black hole which is about 60 times the mass of our sun. It's easy addition. But since that time, they've detected about 5 other of these merging black hole systems, okay? Which is very exciting. We're starting to get statistics. But none of these black hole mergers, as far as we can tell, emitted any light. And that's for the simple reason that black holes are pure space-time, okay? There's no matter around. Matter is what emits light, okay? We can emit light, the sun can emit light, there's matter there. Black holes are just 2 holes in space-time that merge to create a new hole in space-time. So they don't emit any light, and so we can't confirm, independent of what LIGO detects, that that's what was going on, okay? We believe LIGO, it certainly looks exactly like what Einstein predicted, but we have no independent confirmation. But there are other objects which can undergo this same death spiral. In particular, these neutron stars, which I talked about, can also find themselves in binaries, and they also emit gravitational waves. And as they emit gravitational waves, they spiral together faster and faster and faster, and near the end, they're moving almost at the speed of light, and then they collide in a catastrophic collision, which you'll see at the end here, animated. Okay? And this includes actual matter, not just space-time. There may be some light that's produced by this event. Last August 17th, 8:41 in the morning Eastern Time, the LIGO detector, Livingston detector, and Italy's detector Virgo were on. And this is showing what signal they detected. This is the frequency of the gravitational waves, and you start to see a track appear here. This is the beginning of a chirp. There it goes, there it goes. You start to see it weakly in the Hanford detector. You can kind of see it. You would have barely been able to hear it, but right there is a neutron star merger. Okay. Black holes merge very quickly because they're very massive when they come into LIGO's observing band. But neutron stars, they take a long time and they merge. And this was extremely exciting discovery, sent them from 2 neutron stars. And again, what's happening is the gravitational waves are distorting space-time, and when that goes through one of these detectors, they see the signal. Okay. But there's something more, which is we would like to know where in the universe, where in the heck did these things come from? And the way we do this is through something we call triangulation. It's the same basic thing that how GPS works. You have a source of gravitational waves which is far away from the Earth, and the gravitational waves pass through the Earth, and you can measure the time delay between when they arrive in Louisiana and when they arrive in Washington State, or when they arrive potentially in Italy. And, and based on that arrival, you can time the arrival of the gravitational waves and pinpoint back where on the sky this thing came from. And that's what LIGO did. And after this merger of neutron stars last August 17th, they pinpointed the direction towards the constellation Hydra. Okay? And they told the astronomers within a few hours look in that part of the sky, you might see something interesting, because we just think we saw 2 neutron stars merging. And so this launched an epic follow-up campaign. Basically, every telescope in the world at every frequency you can imagine all pointed towards the constellation Hydra to try to see if there was any glow from this merging neutron star. And this is basically telling you how things unfolded. So in addition to telescopes we have on the ground, like this one or this one, which you're familiar with, optical telescopes, we have telescopes in space, for instance, gamma ray satellites like NASA's Fermi Gamma Ray Satellite. And essentially, we saw this neutron star merger at all wavelengths. We saw gamma rays from it, we saw visual light from it, we saw X-rays from it, we saw radio waves from it. But I'm going to tell you how the first basically day, what took place. So this is the sky. What actually happened is within 2 seconds of the merging neutron stars, the Fermi satellite saw a burst of gamma rays from this part of the sky. There was another satellite called Integral, which also detected a burst of gamma rays from this part of the sky. So now we know it's coming from this part. Then LIGO said, this is where we think the gravitational waves came from. It could be here or it could be here. But then the Italian observatory chimed in and said, it's in this region. And what you're seeing are all the galaxies in that direction. And after some efforts, visual telescopes found within one of these galaxies, this particular one we're zooming in on right here, they found a fading source of light. So I'm going to show you that movie one more time. Let me explain it one more time. So, oops. So LIGO detects a burst of gravitational waves. Within 2 seconds, a burst of gamma rays comes from this part of the sky. Then LIGO looks at its data and says, where did we see these gravitational waves coming from? And they were able to localize on the sky, to this region. And then the Italian Gravitational Wave Observatory analyzed its data, and we localized to this region. And we're zooming in on all the galaxies in that part of the sky. And the one in which we ultimately found the signal was the one we're zooming in on, NGC 4993, at a distance of 130 million light years. This sounds like a long distance, but it's actually within our backyard. We can see galaxies to many billions of light years. So this was surprisingly close. So this is the galaxy. So what happened was this event happened over the Indian Ocean. And all of the big telescopes on Earth are in Chile. So everybody had to wait 11 hours for the Earth to rotate so it would get dark in Chile so they could observe. And so they got on about a half a day after, and they detected this fading glow here, and then they followed it over the ensuing week. And so you're seeing the half a day, a few days, a week, this fading point of light. I was involved with one of the groups that followed this up with the dark energy camera, again located in Chile. The most amazing thing about this for me was that when we saw this, I understood what it was. I understood why neutron stars merging should give us this fading light. And so that's the story I want to tell you now, and the story of how this connects to the origin of gold. So when 2 neutron stars merge, it's a messy process. The 2 stars are merging from gravitational waves. They come together and they collide at an enormous velocity. And this produces an enormous cloud of debris. It produces an object which ultimately collapses into a black hole in about 100 milliseconds. And then there's a disk of material around the newly formed black hole, about 1/10 of our sun's mass in material within about 30 kilometers, a swirling sort of mess of material. And it turns out that black holes are kind of fussy eaters. So only a little bit of this matter will make it into the black hole. A lot of it is expelled from this event, flung off into space at a fair fraction of the speed of light. And this material, as you might expect, since it comes from a neutron star, is extremely rich in neutrons. So as it decompresses, you create these heavy elements like iron, and you have so many neutrons that you just bombard them with neutrons. This is alchemy. This is how we create the heaviest elements is by bombarding lighter elements with neutrons. And this is exactly what happens in the material that is ejected from a neutron star merger. So this is an iron nucleus, and now we're bombarding it with neutrons and creating a heavy nucleus. But an unstable heavy nucleus, one that is not is radioactive. And so now it's undergoing a radioactive decay at the end. So within a few seconds after this cataclysmic event, we created a whole swarm of heavy elements like gold and silver and platinum, but they were all radioactive. And that's important because if material is radioactive, then it releases heat, and heat can produce light. And light is how we see this thing so far away. And so this was a prediction that I made in a paper in 2010, where we basically calculated how bright this afterglow of a neutron star merger would be as a function of time after the event. And what we found when we did the calculation is that it would be about 1,000 times brighter than what we call a nova in our galaxy. And so the prefix kilo means 1,000. That also has connotations with respect to gold. And so we called this a kilonova because we were predicting it would be 1,000 times brighter than a nova, and it would start fading about a day after the merger following the radioactive decay of these heavy elements. So essentially we're creating a debris cloud of radioactive material and spewing it into space and looking at the glow from it. So it's like an enormous atomic bomb of sorts that as it expands produces the light that we observe. And this is what we saw after this neutron star merger. Within a half day they got on and saw this fading glow. And if I took our model from our 2010 paper and overplotted on the data that was taken by the astronomers last August, it had a remarkable agreement with the theory. And so there's some details at the end where it doesn't agree, but that's for another reason I could go into. But this was amazing to me. I mean, we're thinking about something, working on it on our computers, in our heads, at the blackboard, and then nature does it and lifts the curtain and it agrees with your theory. Very exciting for me. Probably an experience that most scientists have at most once in their life. So let me show you NASA's impression of this entire crazy event. Apologize for the music. So the two neutron stars are merging. They're going to coalesce and create this jet from the black hole, which produces the burst of gamma rays. And then there's a cloud of debris which comes out and is the radioactive material that we saw producing these heavy elements and ejecting them into space. And this is the jet of the gamma ray burst. So I could show you that one more time, I guess. So two neutron stars in spiraling. The final few orbits take just a few milliseconds. This is so fast, you can't even imagine, but there's so much energy released, it's unfathomable. And you make a black hole, create a jet of material, and then there's this radioactive glow, which becomes red at the end, which is another story. It becomes red because it has the heaviest elements in it. It's a fascinating story. So we think that we have found an origin in nature of the heaviest elements. We now have an idea where the bottom of the periodic table came from. This was an old mystery going back. So in the 1930s, Hans Bethe discovered the fact that the sun is powered by nuclear fusion, and people started thinking about how the heaviest elements are created. So there was a famous paper by the Burbages and Fred Hoyle and Willie Fowler in 1957. And they identified that somewhere in nature there is a very neutron-rich site that is making the heavy elements, but they didn't know where it was. And now we think we found it. This single event, which we call GW170917 because it was a gravitational wave event discovered in 2007 on August 17th. Actually, it should be 0817, sorry. So this event ejected a total of about 5% of our sun's mass in these heavy elements. Of that material, we think that this about 10 times the mass of our Earth was created in gold, 50 times the mass of our Earth created in platinum, and 5 times the mass of our Earth created in uranium. So neutron star mergers are rare events, okay? Supernova happen once every century in our galaxy. Neutron star mergers happen once every 10,000 years. The only way we were able to detect this event is looking beyond our galaxy to the many other galaxies which are out there. But if you take, even though they are very rare events in our galaxy, if you take how much this event produced and you multiply by that rate, what you find is that prior to the sun's formation, there were enough neutron star mergers in our galaxy that you could create most or all of the precious metals that exist on our Earth. So of course, the way this happens is the neutron stars merge, they eject material, it mixes with the gas in our galaxy, dilutes the gold so that it's not so concentrated. That diluted material ultimately collapses to form another generation of stars which have planets, and those planets have more gold and platinum on their surfaces as the result of these merging neutron stars. So we now think we understand where the bottom of the periodic table comes from. This was a figure that was created in 2008 when I started my PhD. And what you can see is that the blue elements here are labeled supernova up here, because at that time people thought that these elements came from supernova. We have since revised this figure as a result of this discovery and others that we now think that the bottom of the periodic table may come from merging neutron stars, although I do think this is a little premature to assume that they're the only place in nature this can happen. But it's clear that at least one site for creating these heavy elements is in these cataclysmic events that gravitational waves pointed us to. So this was exciting. I coined this term kilonova in a paper we wrote, so it was very exciting to see it on the cover of Nature, which is the most prestigious journal in science, essentially, and this amazing illustration that someone made of merging neutron stars. I was also honored to win this award as a result of this work, but I really want to emphasize that this was an amazing group effort. You had all of the people in LIGO that toiled for 20 or 30 years to build this sensitive detector to see merging neutron stars. You had myself working on theory, but you also had many other theorists who contributed to our understanding of this event. And you had all of the astronomers who, on that morning in August and evening in August, were able to point their telescopes to the right part of the sky and make this discovery. But this is me receiving this prize, which is actually a wormhole. So it's like it looks like a sphere, but there's like a little wormhole in the middle. And I got it from this guy, Edwin. I sort of half joke, but he's kind of considered the smartest guy in physics. He's like the new Einstein, I guess you could say. So it's quite an honor to receive the award from him. There's a few humorous things and then I want to kind of finish up because I want to take some questions from you. So one of the members of our discovery group pointed out to me in an email just a few weeks ago, I came across an interesting passage in a Star Trek book that I was reading, which said, colliding neutron stars have never been observed by Starfleet, as this event is thankfully rare. The amount of energy released in a possible neutron star collision would be enough to sterilize all life within a few thousand light years of the event and cause extinction events in thousands more. So my colleague said, this is very exciting because we are 400 years ahead of Starfleet scientifically, which means warp drives, replicators, and a utopian post-scarcity economy are right around the corner. The LIGO Observatory is operational in Hanford and Livingston. They've shut down for upgrades. They're going to turn back on in March. The Italians have the Virgo detector. LIGO is constructing another detector in India, and the Japanese are just constructing a detector called Kagra. And so when LIGO, this observatory, turns back on, it will be more sensitive to mergers, meaning it can detect neutron star mergers from further away in our universe. And in fact, that means that the rate at which we detect them, because there's more universe out there the further we could see, we will see these events more frequently. So rather than seeing one every few years, we will see maybe once every month. And so we're going to see a much wider variety of these systems. We're going to see different types of neutron stars colliding. We're going to see the same event from different angles. It's going to be very exciting. And we may discover new events. For instance, what happens when a neutron star merges with a black hole? Will the black hole swallow the neutron star whole, or will it tear it apart and produce one of these luminous events? This is a very exciting time to try to probe the properties of black holes through their gravitational waves and light. And all of this is going to happen within the next decade. So I just want to say that this is, really the way science works. It comes and starts and fits. But we really rely on the discoveries of the past to build to our new future. So I just wanted to go through very briefly the kind of, what brought us to neutron star mergers. We had Newton developing his theory of gravity. We had Einstein developing the theory of general relativity. We had Hans Bethe understanding that the light elements are created inside of stars. We had Oppenheimer and his student recognizing how stars form when massive black holes, how black holes form when massive stars die. We had the Burbages and Hoyle and Fowler identifying that the heavy elements come somewhere in nature that's not inside of stars. We had Jocelyn Bell discovering neutron stars. We had Kip Thorne and Ray Weiss coming up with, motivated by the discovery of two neutron stars in a binary, coming up with a detector that could detect those gravitational waves, which finally came to fruition last August. At the same time, we were undergoing a revolution in astronomy to where we can now view large parts of the sky simultaneously, in part due to the advent of CCD cameras. So it's really humbling to be part of such a great and building picture. And it's important to emphasize that these discoveries made by people from a variety of different backgrounds, but also there's some objective truth to them. They don't the fact that the neutron stars merged. We agree upon it, even if we disagree about other things. Okay, so I just wanted to send out a thank you to my group. I have a number of graduate students and postdoctoral researchers who work on this problem, and my job would be impossible without them. And so this is my group at Columbia from last year. You should know that this research is generously supported by your tax dollars. When you support NASA or the National Science Foundation, it's research grants to them through us that allow us to work on the predictions and the understanding of these phenomena. And you might not see the immediate practical benefits to trying to understand merging neutron stars, but at the very minimum, we create students and individuals that can think and analyze problems, and wherever they end up in academia or elsewhere, they contribute positively to our society. And so, this fundamental science is extremely important. And it also motivates, many young people to go in directions that are beneficial for our society. So I just want to conclude by sending out a few special thanks. I want to thank the John Whitty Foundation for supporting this lecture, Des Moines County Conservation Society, I suppose, and Jim and Judy Hilkin personally for getting me to come, and of course the Southeastern Iowa Astronomy Club. And I want to thank my wife and daughter for coming to Iowa, which of course they enjoy. But they were not able to be here tonight because it's past my daughter's bedtime, and my wife and father my mom and dad for putting me up while I'm here in Burlington. So, so with that, I will finish. Thank you. Okay, so now I think we're going to raise the lights. And if you have any questions, don't be shy. There are no stupid questions about anything. I'm happy to take them. I can't see a particular, okay, I see somebody in the middle there, yeah. But maybe, yeah.
Is there any significance to the location of the LIGO detectors?
Yeah, so the question is if there's any significance to the location of the LIGO detectors. I don't know the history of this. I think it's a combination of scientific considerations and political considerations. But we want them to be far apart as possible so that we have the largest baseline in order, if we see some kind of blip, the reason we have two of them is if you see some kind of blip in one, it might not be real. But if you see that same blip and then, a millisecond later in the other detector and they're identical, then it's pretty confirmed that that's a real source. And so we want them to be far away so that they don't see the same sources of local noise. But specifically why they're in Washington and Louisiana, I'm not sure. It's probably having something to do with influential senators, but I'm not sure.
What's the speed of the gravitational waves?
So the gravitational waves move, as far as we can tell, at exactly the speed of light. So and this event actually provided us one of the most stringent constraints on their speed, because we saw within 2 seconds of when the gravitational waves arrived, we saw the gamma rays. And we think the gamma rays were produced intrinsically by the event a little bit after the merger. So basically we know that gravitational waves and electromagnetic light travel at the same speed to within 2 seconds over 130 million light years. So it's almost exactly at the same speed.
Has the confirmation of gravitational waves done anything to advance the unification of quantum mechanics and general relativity?
Unfortunately, I'm not the best person to answer that question in detail. We still are struggling to unify quantum mechanics and general relativity. So I would say that there are some theories that would try to unify them that this event could rule out, meaning that there are some ideas people have had for how to unify them that the fact that the gravitational waves behaved according to general relativity basically rule out that there were significant effects of quantum mechanics. But by and large, no, unfortunately. These are very large macroscopic objects, so the quantum mechanics doesn't come in too sensitively into this. Yeah.
What range of frequencies do you find in gravitational waves?
I'll go back and show you. They're mostly in the range of tens or hundreds of hertz.
Do you only get the very low, very high frequency with the most energy?
Well, I wish I could turn off the sound here, but see, what did I do with my pointer? Anyway, so this is 50 hertz and 500 hertz. That's where most of the sensitivity of LIGO is between about 10 hertz and a few hundred hertz. And so the neutron stars are merging. They're coming in at about 40 hertz, and now they're getting higher and higher in frequency. And then the end of the in spiral, where they start to lose signal, is up here at about 400 hertz. So there are more cycles of the merging stars at low frequency, so they pick up a lot of the signal down here. And then it's true that the signal gets stronger as they go up in frequency, but there are fewer cycles. So much of their ability to detect this comes from the lower frequencies. Does that help?
I would think that you would get hundreds, if not hundreds of thousands of these blips a second.
You get lots of noise, but neutron star mergers are rare. Real events, you get lots of blips, but they have very sophisticated techniques to tell if those blips are real. So they can look for a blip in the one in Louisiana and look for a blip in Washington, and unless they're just timed the right way, unless they look like the same blip, then they just throw it out.
So I have a question in regards to scientists around the world.
Yeah.
Different countries, different languages, but you're all speaking the same science language.
Yes.
But you're controlled by politics for the region. and funding and things like that.
Yeah, yeah.
And how does the science community interact with the different geopolitical issues? So when something like this comes around, you have what, a few milliseconds for the entire world to point everything that way and take a look at it. How does all that work? That seems like a
We try to be, we try to be, yeah, yeah. With this first event, LIGO didn't announce the discovery immediately, openly, but what they had was a call. So any group of observing astronomers, so if you had a telescope, maybe even a backyard one, although I don't know to what extent they allowed amateur astronomers, but basically anyone who had a telescope, didn't matter what country you were from, if you signed an agreement with them that when they detected it and they told you about the event, that if you didn't publicly disclose that discovery before they wanted to disclose it, you could get this alert. So there wasn't any, strong issue there. I think, you know, broader in broader terms, I mean, it is sometimes hard to create collaborations that transcend, transcend countries. Right now, it would be hard for NASA to, work with the Chinese or something to do some type of mission like this. But we try to keep, and that's sort of one of the issues. But a lot of the philosophy is that when you make a discovery, the data should be open. You may not make the technology that you use to do the discovery open to everybody, but there's clearly a scientific cost to holding this type of discovery, within your group. If you don't tell everybody, you might miss an opportunity to get maybe somebody in a different country has a telescope that's in the right place at the right time. So I think there's a general acknowledgement that the discovery should be open, even if the technology is still, kept under wraps. Yeah.
Brian, when you observe the signal, are these observed by people physically observing this, or is it computers detecting anomalies, or how do they actually?
Yeah. So the gravitational waves are, it's mostly done by computers. So they're measuring the distance of the mirrors and they're trying to compare how the mirrors are shaking to different predictions for these inspiraling binary neutron stars. But when it comes to the telescope follow-up, the optic, there usually is someone literally at a telescope that is, in Chile who's that night is observing and, is telling the computer to point the telescope a different direction. I mean, So there is somebody on site when we're talking about the telescopes. The satellites in space, then they have to transmit up the signal, to point the satellite somewhere else. So most of the astronomical observations are done by people or people that are directly controlling the telescopes. LIGO itself, this gravitational wave observatory, it's always analyzing the signal continuously, and when it sees a gravitational wave, the computer basically tells a human, so it wakes up some human and says, we have a possible detection, and maybe 90% of the time it ends up being a false positive, being something that's not real. But then the discoveries are kind of vetted by humans, which then pass it off to the astronomers.
Brian, do you work with tertiary stars at all, or such a thing? And have you observed weirdness with 3 versus 2?
There are tertiary stars. There are 3 stars. So you have 2 stars that are orbiting each other, and then there's a third one going around the outside. Or you even have cases with 4 stars orbiting each other. But it's very unlikely that you would have 3 stars that are kind of merging at the same time, through gravitational waves. So it's possible that these merging neutron stars, for instance, there could be a third star that's orbiting both of them, but it would be hard for us to see that in the signal. But yeah, exactly. Triple stars and quadruple stars exist. They're actually surprisingly common. Yeah. All right.
So going back to the frequency question, do you see the same type of frequency shift over distance that you do with light with the gravitational waves?
You mean like if I have light that's very distant, and as it travels through space, it gets shifted by the expansion of the universe? Is that what you mean, or?
Similar to that, yeah.
Yeah. So you see the same effect. So gravitational waves. So if you have light that comes, so let's put it this way: if you have a blue star, and I move it far enough away into the distant universe, it will actually appear red, because the light coming from the star to Earth is being stretched out, if you will, by the fact that the universe is expanding. So blue light can be stretched into red light if you have an object that's far enough away. And it's just true with gravitational waves too, that the frequency of the gravitational waves is decreased if you had a merging star that was happening very, very far away. So kind of giga light years away, as opposed to just millions of light years. Yeah. But
Hey, brother.
hi, how's it going?
All right. So, my question is, you had a slide where you were showing, I'm guessing it was the two black holes where they were spinning around even closer and closer.
Yeah.
To the point, right? So you said when they combine, there's no light coming from it. So maybe you can make like an educated assumption or something. What would it take for light to come from that? Will light ever come from?
From two black holes, or?
Yeah.
Yeah, so if there's no matter around, the prospects are not very good for making light from these. Black holes emit light, but through Hawking radiation, but it's extremely weak, and you can never detect it. So what you need if you want black holes to make light is you need a way to have them merge in an environment which has a lot of gas around. So if you had, for instance, a big star that collapsed into two black holes, and if the two black holes merged inside of a star, then there might be some matter that would get heated up by that process to emit light. But you need to come up with a pretty contrived scenario to make black holes produce light. But we're going to keep looking. So I didn't mention, but we actually have looked with telescopes at all of the black hole mergers, and so far we have seen nothing, because we don't expect to see anything. If we did see something, that would cause us to really scratch our heads, because we don't. But that's what you hope for in science. Is not you don't actually hope for what I have, which is, for confirming a prediction, because you kind of hope. I hope for it, but what you hope is to be surprised, because then it means you don't understand something, and that usually teaches you something new. So if we saw light coming from merging black holes, then we'd be like, whoa, what's going on? It's something new.
I have a question. I was surprised to see in the little presentation the two black holes that were gravitating together, and one seemed much bigger than the other one. Is it something that is, I would imagine that one would absorb the other one by being bigger, or?
Yeah, black holes can come in different, so the size of a black hole, its event horizon scales with its mass. So I think in that movie you were seeing a black hole one that had a higher mass than the other. And then they merge, and it's true that when they, you can kind of think of the less massive one as falling into the more massive one. And then at the end they make a black hole which is, roughly speaking, the sum of the two initial masses. So if you took a black hole with 30 times the mass of our sun and merged it with one that was 10 times the mass of our sun, you don't end up with one that's 40 times the mass of our sun, because gravitational waves carry away a little bit of mass, because mass is equal to energy. That was something else Einstein told us. So gravitational waves carry away energy, so you merge a 30 and a 10 and you end up with a 39 or something. But yeah, so they do. Yeah, the bigger one will eat the smaller one. Only when they get close enough, though. Yeah.
Does any of the new data suggest an energy range for searching for gravitons?
Wow, I don't think this data says anything new. Gravitons are extremely low energy particles. So I don't think it's really telling us a whole lot new. They're really hard to detect, and they're still hard to detect. Yeah. Question?
A couple questions. Do you believe now that none of these heavier elements are created during the collapse of a supernova?
I don't. I think that's still possible that supernova could produce some of them. What we have growing evidence for is that not all supernova produce them, or at least the major source that produces these elements are not your typical supernova. I do believe that there are exotic types of rare supernova that could also produce these neutron-rich conditions. But I think what we could say with this event is that with some high confidence, a fair fraction, if not most, of these heavy elements come from merging neutron stars. Whether that number is 10% or 90% or 99% or 100%, we can't say because we just have one event. But I think it's, so if it ends up being the case that we don't have quite enough with these merging neutron stars, we're going to have to go looking for additional sites.
When you were making your prediction, I would assume that you had a lot of math for doing that. Did you have to take into account quantum entanglement or superposition for your math?
No, most of what we do, what I do, is pretty classical physics. It's mostly hydrodynamics. I guess you take into account indirectly because it's a lot of nuclear physics. So you need to know if I have an atom and I hit it with a neutron, like what is the probability that neutron will be absorbed or something. So I guess there's quantum physics there. But what we're doing in astrophysics is a lot of actually fairly practical physics, meaning we have hydrodynamics and we have aspects of nuclear physics. I mean, what was important in this case was I didn't have the expertise to do the calculation of this nucleosynthesis. I had to get in touch with some Germans who were experts in that. And that's an important other lesson, which is you rarely have all the tools you need. And it's also part in science to try to have enough peripheral vision of what you need to bring in those team members that can provide that additional expertise. So in my case, I had to bring in some nuclear physicists to really make these predictions. You want to come? Want to come out and hang out in New York? Come hang out in New York. It's cheap, I tell you. No.
So I have another question for you.
Uh-huh.
I've been trying to make some visual sense of this. You had a slide where it showed like the world as it spins and its mass, it makes things move around it. And then you had another picture, there were three objects. One was a little bit deeper and then one was really low.
Yeah.
And you're saying it's making things move around it or go on? How does that work? Because one was so heavy, it's so deep, what does it do?
Well, it just is ways. If it goes so deep, it's just a way of saying if you get too close, you're not coming back. But I mean, it's hard to visualize because you're trying to visualize a three-dimensional warping of space with a two-dimensional picture. So you're trying to visualize is the way that objects curve the space-time around them, so the visual you should have is that objects are basically like marbles, like this, the Earth orbiting the sun is like a marble rolling around, this sort of indentation that's created by the sun. And if that hole is too deep, then your marble will fall in. It won't be able to just orbit around. So that's the bit. But the problem is you have to think about it three-dimensionally. It isn't just a two-dimensional problem.
Brian, what research are you working on currently?
Well, I have my group is continuing to work on these merging neutron stars. I work on other events like what happens when a star in a galaxy comes too close to the black hole that's in the center of galaxies. So you might know most galaxies have very supermassive black holes in their centers. Our own galaxy has a black hole in the middle that has about 4 million times the mass of the sun. So another thing I think about is what happens when stars get too close to those black holes. We can see flares of emission that come from deep space, which we think are these disrupted stars, stars that are being voraciously consumed by supermassive black holes. So I think about those. I think about what happens when a object called a white dwarf and a neutron star merge. I like to think about a lot of catastrophic things. But this is a general thing. I mean, we're entering a new phase in astrophysics where we don't just have images of the night sky. We could see images of the night sky like a movie. We could go out and look, and we see it 1 hour, and then we see what it looks like the next hour. And so you see things that appear and fade. And so we're exploring, new types of rare catastrophic events that we previously didn't have any data on. And so I try to get ahead of things. I try to say, what is happening out there that we should be able to go find? And what is the physics of that? What is the prediction to be made?
Right.
Yeah.
How did the gold and the heavy elements end up on our planet, and is it on every planet in the whole universe? Those same elements.
Yeah, I think the expectation is so let me put a few numbers in perspective. So the sun was formed roughly 5 billion years ago. The galaxy's been around for about 14 billion. So there was a good 5 or 10 billion years prior to when the sun formed that the galaxy was around. Neutron star mergers happen in our galaxy about once every 10,000 years. So prior to the formation of the sun, there were about 100,000 neutron star mergers that took place at our galaxy. And every one of those did this, ejected some gold into space. And there's gas between the stars. We call it the interstellar medium. And the gold gets ejected into the interstellar medium, and then there's turbulence in the interstellar medium. It gets mixed together. So this is extremely rich in gold, but then it gets mixed with a bunch of material that has no gold in it and creates a lower concentration of gold. And then that interstellar medium of gas finds its way into stars. So a big clump of it gets together, collapses to form a star, which we call the sun. And that sun has a disk of matter around it, which form the planets. And those planets have gold on it because at some point in the past, there were many neutron star mergers. And so we think that, by and large, the stars, this gas is pretty well mixed in the interstellar medium. So by and large, stars that formed around the same time in our galaxy as the sun have basically the same amount of gold. But if you go back to the very beginning of our galaxy, when there were just a few stars around, the amount of gold on their surface is very significantly more. So you have one star that has a lot of it, and another has none at all. And that's just the kind of stochasticity of these events. If you happen to be a star that was near a neutron star merger, you get more gold. If you happen to be on the other side of the galaxy, you get less. So most stars have an equitable amount of gold, but in the early history, if you were a star formed very early in the history of our galaxy, you might have more or less.